Welcome back to our series on non-parametric statistics. In the previous video, we studied the chi-square test of independence, where we examined whether two categorical variables were associated. In this video, we will study another important application of chi-square, the chi-square goodness of fit test. The basic question is very simple. We observe certain frequencies in our data, but do these observed frequencies follow the distribution that we expected? Before proceeding, let us use our 30-second decision tree. Ask yourself one simple question. How many categorical variables are involved? If there is only one categorical variable and you want to compare observed frequencies with the expected frequencies, use the chi-square goodness of fit test. If there are two categorical variables and your objective is to test whether they are associated or independent, use the chi-square test of independence. This distinction is extremely important. One categorical variable, goodness of fit. Two categorical variables, test of independence. The words goodness of fit may initially sound technical, but the idea is quite simple. We have an expected pattern. Then we collect actual data and obtain an observed pattern. The test examines whether the observed distribution fits the expected distribution reasonably well. Small differences may occur simply because of sampling variation. But if the differences are too large, we may conclude that the observed distribution does not fit our expected pattern. Let us take a simple business example. A company offers 4 products: product A, product B, product C, and product D. 100 customers were asked to select their preferred product. 40 customers select product A, 30 select product B, 20 select product C, and 10 select product D. The company wants to know whether customers have equal preferences for all 4 products. At first glance, the frequencies appear different. But remember, statistics does not make a decision merely by looking at numbers. We need to determine whether these differences are statistically significant. Now let us formulate our hypothesis. The null hypothesis states that customer preferences are equally distributed among the 4 products. In other words, no product is particularly preferred over another. The alternative hypothesis states that customer preferences are not equally distributed. Notice that we are examining only one categorical variable, product preference. Therefore, this is a goodness of fit problem, not a test of independence. These are our observed frequencies. Observed frequency simply means what we actually found in the data. 40 customers preferred product A, 30 preferred product B, 20 preferred product C, and 10 preferred product D. In the chi-square formula, observed frequency is represented by the letter O. Now we calculate the expected frequencies. Our null hypothesis states that all 4 products are equally preferred. We have 100 customers and 4 products. Therefore, under the null hypothesis, we expect 25 customers in each category. Our 100 divided by 4 gives 25. So the expected frequency for product A is 25. For product B, 25, for product C, 25, and product D, 25. Please remember, expected frequencies come from the null hypothesis or from a theoretical specified distribution. Now place the observed and expected frequencies side by side. Product A, we observed 40 but expected 25. Similarly, for B, we observed 30 but expected 25. Product C, we observed 20 but expected 25. And product D, we observed only 10 but the 25 were expected. The question is not whether differences exist. Clearly, the differences exist. The statistical question is, are these differences large enough to reject the null hypothesis? For that, we calculate the chi-square statistics. This is the chi-square formula. For every category, we calculate the difference between observed and expected frequencies. We square this difference, then we divide it by expected frequency. Finally, we add the values for all categories. Why do we square the differences? Because some differences are positive and others are negative. If we simply add them, they could cancel each other. Squaring ensures that every deviation contributes positively to the chi-square statistics. The procedure is not different from chi-square test of independence, but the procedure is almost same. Let us manually calculate the contribution of product A. The observed frequency is 40 and expected frequency is 25. The difference is 15. We square 15 and obtain 225. Then we divide 225 by expected frequency of 25. The result is 9. Therefore, product A contributes 9 units to the total chi-square statistics. We repeat exactly the same procedure for every category. Here is the complete calculation. Product A contributes 9, product B contributes 1, product C also contributes 1, and product D contributes 9. When we add these 4 contributions, the chi-square statistics is 20. Notice something interesting. Product A and product D make the largest contribution. Why? Because their observed frequencies are furthest from the expected frequency of 25. This is how the chi-square statistics captures the overall discrepancy between observed and expected frequencies. We also need degree of freedom. For a simple chi-square goodness of fit test, degrees of freedom are calculated as the number of categories minus 1. We have 4 products categories, therefore 4 minus 1 gives 3 degrees of freedom. But in case of chi-square of independence, we calculated the degree of freedom row minus 1 into column minus 1 because we had rows and columns of 2 different variables. Degrees of freedom are required when determining the probability associated with our calculated chi-square statistics. Our calculated chi-square statistics is 20 with 3 degrees of freedom. The p-value is less than 0.001. Since the p-value is below our conventional significance level of 0.05, we reject the null hypothesis. We conclude that customers' preferences are not equally distributed among the 4 products. In simple language, customers do not prefer all products equally. Now let us perform the test in SPSS. We could enter 100 individual observations, but as we learned in the previous video, there is a much more efficient method when summarized frequency data are available. Enter 4 rows. First variable identifies product category. Second variable contains frequency. Then select data, weight cases, and weight the cases by frequency variable. SPSS will now treat these 4 rows as 100 observations. This is a very useful technique when working with the published tables or summarized frequency data. Let us work on SPSS. After weighing the cases, go to Analyze, select Non-Parametric Test, then choose Legacy Dialogues and then chi-square. Move the product variable into test variable list. Since our null hypothesis assumes equal preferences, select option that all categories are equal. Then click OK. SPSS will calculate the observed frequencies, expected frequencies, chi-square statistics, degree of freedom, and significance value. Work on SPSS.
We started SPSS and entered 2 variables, product and frequency. We have got the frequency of product A 40, product B 30, product C 20, product D 10. As we learned in our last video, whenever there is a frequency, we will have to go to data, weight cases by frequency. So we will enter frequency here. We will say OK, and there will be output weight by frequency. We don't need it. We will delete this output. That is not required. Next, we go to Analyze. Then we go to Non-Parametric Tests, Legacy Dialog, and then we select chi-square. In the chi-square, we put this frequency as a test variable, and we say all categories are equal, and exact and all this is not required. There is no need for any options and all. So we will keep it as it is. Get from data, all categories are equal. We'll say OK. And we have seen the observed frequency and expected frequency. So observed frequencies are 10, 20, 30, 40, and expected frequencies are 25, 25, 25, 25. Now chi-square is 20 with the p-value 0.000. So it means we reject the null hypothesis and accept the alternate hypothesis that there is a difference from the original frequencies. We reject the null hypothesis that observed frequencies are equally distributed. Actually, the p-value says or significance value, whatever is written in the SPSS. So we say it is not equally distributed.
We have Let us examine the SPSS output carefully. Observed N represents the actual frequencies. Expected N represents the frequencies expected under null hypothesis. The residual is simply difference between observed and expected frequencies. Then SPSS reports the chi-square statistics, degree of freedom, and the significance value. Do not simply look at the p-value. Look at the entire output and understand how observed frequencies differ from the expected pattern. Now let us perform the same analysis in Python. We import the chi-square function from SciPy. Please notice carefully, this is a chi-square function, not chi2 contingency, which we used for chi-square test of independence. We create one list containing the observed frequencies, another list containing the expected frequencies. The chi-square function returns the chi-square statistics and the p-value. The distinction between the two Python functions is important.
I have already started the editor Jupyter and written the Python commands from scipy.stats import chi-square. It is not chi2, it is chi-square. Observed values are 40, 30, 20 and 10, which we have put in the square brackets. Expected values we have written ourselves 25, 25, 25. So we are going to find it chi2 comma p and it is equal to chi-square f observed values is equal to observed f underscore expected values is equal to expected. And then we close the bracket, print chi-square, chi2 and print p-value p. It will take some time to import chi-square. We will run this cell and see the output. Now the chi-square is 20, p-value is 0.000169, so many decimals. If you want, you can round it. As I told you in my last video, you can round it also, round comma 3 up to 3 decimals and then close the bracket again. So 2 brackets open, 2 brackets close, and now we will run it again. So p-value is 0.000 and it says that we have to reject the null hypothesis and accept the alternate hypothesis, which says the observed values are not equally distributed.
After working on Python, see, Python gives us a chi-square statistics of 20. The p-value is approximately 0.00017. Therefore, it is clearly below 0.05. Therefore, it will reject the null hypothesis. Notice that our manual calculation, SPSS analysis and Python analysis all lead to the same conclusions. The comparison must be absolutely clear. The chi-square goodness of fit test involves one categorical variable. It compares an observed distribution with the expected distribution. The chi-square test of independence involves two categorical variables. It examines whether the two variables are associated. The mathematical foundation is similar, but the research questions are different. At this stage, I would also suggest watching my videos explaining association and correlation. Researchers sometimes use these terms interchangeably, but statistically they have different meanings. Correlation is generally used to measure the direction and the strength of relationship between numerical or ranked variables. Association is commonly examined between categorical variables. Understanding this distinction will help you select the correct statistical test instead of simply following a software menu. Let us discuss some common mistakes. The first is confusing the goodness of fit test with the test of independence. Second is entering the percentages when the analysis requires frequency counts. The third is using incorrect expected frequencies. Another important problem is very small expected counts. Finally, do not perform a goodness of fit test without clearly defining what the distribution is expected under the null hypothesis. The expected distribution must come from theory, a stated assumption, or a specified model. Welcome to the Researcher's Corner. A good researcher does not stop after finding a significant p-value. First ask, where did the expected distribution come from? In our example, we assumed equal preference but in real research, expected proportions may come from theory, previous research, and market share, or a known population distribution. Second, examine the expected frequencies. Third, ask whether statistically significant difference is also practically meaningful. And finally, examine which categories make the largest contribution to the chi-square statistics. In our example, product A and D contribute much more to the chi-square value than product B and C. The p-value tells you that a difference exists. A researcher goes one step further and asks where the difference is coming from. This is how the result can be reported in the thesis, dissertation, or journal paper. We identify the test, we clearly state the substantive conclusions, then we report the chi-square statistics, degree of freedom, and p-value. Avoid writing only the result was significant. A complete statistical statement allows reader to understand and evaluate your findings. Let us finish the decision rule. If you have one categorical variable, want to compare observed frequencies with expected frequencies, use the chi-square goodness of fit test. If you have two categorical variables and want to examine association, use the chi-square test of independence. If you remember the simple distinction, you will merely confuse the two tests. Thank you for watching. If this video has helped you understand the chi-square goodness of fit test, please subscribe to the channel and share the video with students, researchers, and colleagues. If you have a question, please write it in comments. In our next video, we will study McNemar tests, an important non-parametric test for paired categorical data. See you in the next lecture. Thank you.
Always share the videos of Dr. Sachdeva to your friends who are interested in data analysis.